Welcome back to ECE 442-542. Now that I have your attention, when the clock strikes 5:30, we know that we have to be quiet so that somebody on the other end of this microphone actually can hear what we're communicating to them, hopefully. We're back in ECE 442-542. Homework number 1 is due the next day that we meet, which is Monday, and that's due not necessarily in class. You have a few hours until it's 11:59 p.m. You can submit it as a scanned PDF on D2L. There's a Dropbox or an assignment folder that you can submit to. If you're trying to access the Shams outline, apparently it's an old enough document that the library and EBSCO host, whatever it is, they're having difficulties. And so I told them about the problem, but in lieu of that, I have scanned example 6.28 that I reference in homework number 1. That's underneath the homework assignment, and you should be able to at least read that part of the Shams outline. Proctor agreement for those that are online, that's due on Monday as well. Homework 2 has now, I believe I've posted that, and that's in Unit 2. And exam number 1 review material, you might start looking to make sure you have access to that it's there, because exam number 1 is coming up probably sooner than we think, and that's the 7th of February on a Wednesday. Make sure you make it to class if you're not coming to class regularly. If you're an on-campus student and you're taking advantage of the recorded information, or at least you're using that, make sure you show up for the exam on that Wednesday. Today what I want to do is finish up our block diagram example that we started last time. We created one in the time domain with an all-delay block diagram. We put that into a state space representation. We didn't quite get finished with our state space representation. We didn't get our output equation. So we'll finish that up, and then we'll show how easy it is, or how straightforward it is, to go from a time domain block diagram into a frequency domain block diagram. And from that, we'll illustrate some block diagram algebra, which you might want for one of your homework problems, homework number 1. We'll use the frequency domain block diagram to find the transfer function of that system. Maybe later in the class we'll actually show how to find a transfer function from a difference equation. But you should be starting to be comfortable, or starting to get comfortable, with making the transformations from all of these different representations. We have difference equations, we have state space representations, we have block diagrams, we have transfer functions. We should be able to chase our tail and get back to one or the other starting from a given representation. That's the idea. Once we've chased our tail enough and gotten dizzy, we'll try to get into the complex frequency variable z. We've just been using it as an operator, as z to the minus 1. Now we'll try to start talking about how is it related to this complex frequency variable s, and if you were comfortable with locations in the complex s-plane corresponding to certain dynamics as far as how quickly a particular response might decay or how it might oscillate, let's see if we can start to get that same comfort level in the z-plane. And we'll talk about this mapping from the s-plane to the z-plane and where that relationship between S and Z actually comes from. I think you already know about discrete time stability. We've talked about that enough, but that will become clear from the mapping. We also have this sampling frequency, and that's related to the fastest set of dynamics in our system. What is the fastest, or what is our closed loop bandwidth? That's what I'm calling omega sub c. This rule of thumb says sample 30 times that in terms of radians per second. We have different ways of referring to sampling. here is where I'm hoping we get to, which is this relationship between a difference equation in the time domain and a transfer function in the frequency domain. How can we go very quickly to that transfer function given a difference equation? Just like when you started with a differential equation, you could find the transfer function by Laplace transforming that difference equation. We will z-transform the difference equation to find the transfer function for our discrete time system. And now we'll be dealing with polynomials, ratios of polynomials in z, or z to the minus 1. It may seem like we're going a little bit backwards, but now that we've started playing with z, we'll define the z transform. And that's really just this summation, this weighted sum of time domain numbers, or this sequence of numbers given by x of n. And x of n could correspond to a signal. It could correspond to a system's impulse response. And we can put both of those into the frequency domain. And what capital X of z corresponds to, whether it's a system or a signal, you'll have to just know or be given or told what does that really correspond to. And then we'll start taking z transforms of common waveforms. An impulse or a pulse, a step, a unit step, exponential, exponentially damped sine wave, exponentially damped cosine wave, etc. We'll get comfortable with taking those time domain waveforms in discrete time into their z transform representations. And that should take us to about midnight, and then we'll be ready to go home, and it'll be warm enough now at midnight it won't be that big of an issue. I know that's all you're worried about is the temperature outside, not how late we're here, correct? We can all walk each other to the car if we're, or our transportation or our bicycles. We'll be safe. How's that? Let's get into what we're supposed to be doing, which is learning about discrete time systems. Here is our all delay block diagram. And how did we generate this? Where did this come from? Do you remember? It came from a different representation. What was the representation that we began with to generate this block diagram? We started with a difference equation. So we had a linear difference equation, and we used that to build up this all delay block diagram in the time domain. So now we have two representations. How did we make or create a state space representation from this block diagram? What's the strategy? How many state variables do I have, or state variable components do I have for this system? 2. Consistent or the same as I have delays. And now how do I find, or how do I define those state variables? And this you'll have to know by at least exam 1 if you don't know it by midnight tonight. Those outputs of the delay blocks allow us, if we simply label these, I think to be consistent with the last time, let's label this as x sub 1 and this as x sub 2. And state space representations are not unique. You could have simply flip-flopped those labels and you'll create another state space representation. It will model exactly the same system, but your representation will be different from what this one would be. But that's okay. State space representations are not unique. But once we have this labeling, then we can go to the input side of each of those delay blocks and write down what that equals, which in this case, this one becomes x sub 1 of n plus 1, and this signal right here is x sub 2 of n plus 1. And now, from that, we can actually write down, if somebody tells us, well, we're assuming that this particular signal is our output for this system. I think that's how we defined it before. Now we can take this and put it into a state space representation, which typically when I say a state space representation, I'm looking for the matrices. But maybe before we get to the matrices, we write it out. In this case, what is x sub 1 of n plus 1? And we want to write it in terms of states at the time index n and the input at time index n. We don't want any delayed versions of the argument or advanced versions of the argument. They have to be at n. What is x sub 1 of n plus 1? We don't have any of x sub 1 of n, do we? Making that up. We're really just asking, what is this signal? What makes it up? What generates that from x1 of n, x2 of n, and r of n? And it's only x sub 2 of n. So that now we can write down, we have x sub 2 of n scaled by 1, and we don't have any input directly impacting x sub 1 of n plus 1. And this is really how x sub 1 of n plus 1's dynamics are generated. X sub 1 of n plus 1 at the next time step is some linear combination of the previous x state variables and the input. What about x sub 2 of n plus 1? Now we're after this signal, which is an output of a summing junction, and we make that equal all of the signals coming in. And in this case, it's r of n. We have a weighting on x sub 2 of n. And here we don't want to call that x sub 1 of n plus 1, because on the right side of the equal sign on the state space, we need those to be at index time n. This is now minus 3 times x sub 2 of n. And minus 2 times x sub 1 of n. And now it should be a straightforward exercise to plug in those numbers in the 6 locations that those go into. The top row is pretty straightforward, and the second row, making up x sub 2 of n plus 1, is minus 2 times x sub 1 of n plus a minus 3 times x sub 2 of n plus r of n. That's where we made it to last time, I hope, if my memory is correct. And now what we want to do is generate the output equation. And these equations all have to be compatible. We have 2 state variables. How many outputs have we defined for this system so far? Just 1. So we have 1 row making up the matrices in this output equation. And if we go back to the block diagram, we simply look and see y of n could be coming out of a summing junction, and if it was, then it would be all of the inputs into that summing junction. We could put in a virtual summing junction right there and say what signals come into that summing junction to make or to create y of n. Just x sub 1 of n, isn't it? There's no direct feed through from the input R over to that, or there's no scaled version of x sub 2 directly going in to build or create y. The output equation then is 1 x sub 1, 0 x sub 2, and 0 r of n. And if we wanted to, we might call those phi, gamma, h, and j. I'm mixing Greek and normal alphabet, but that's okay. These I might call the system matrices. But they each have their own defining phrase associated with each of those four matrices. So here's maybe the confusing thing. Those four as a group are called the system matrices. Phi, that really holds all the dynamics of the system, that's our system matrix. Gamma is the input matrix, H is the output matrix, and J is our direct feed-through matrix. Does everyone see the eigenvalues of phi? Do those just pop out at you? Maybe they will by 10 o'clock tonight. But if we looked at the eigenvalues of phi, those equal -1 and -2. And you should remember those numbers. Those should stand out to you. Those were actually the roots of our characteristic equation. When we found the characteristic equation from our building up the solution of the homogeneous or the non-homogeneous, we came up with that same characteristic equation. And that's really, if you hit that system, either with some kind of input or a pulse, an impulse, that system naturally wants to shake at -1 and -2. And in this class, this is a controls class, we may want to introduce a controller to change those natural modes, because right now they're unstable. We might like to stabilize that system. That's one of our goals eventually. But right now we're just trying to understand what's happening. The eigenvalues of a matrix, our system matrix phi, that's the determinant of lambda I minus phi. We set that equal to 0, and that gives us the exact same expression that we had for our characteristic equation. How big is the I matrix in that expression? Or what are its dimensions? Maybe I shouldn't say how big it is, because you'll be saying, well, yours looks like it's maybe 2 inches by... Yes. It has to be the same dimension as the system matrix, and our system matrix is always square. It's always the same number of rows as columns, which is nice because the identity matrix is always square. And I, in this case, is a 2 by 2. Meaning if you now wanted to, by hand, compute the determinant of this matrix, lambda I minus phi, and here I've tried to put it in as explicit of a structure as possible. You have the scalar lambda, and what we'd used before was maybe z, but I'm just using a different variable here, times the identity matrix, which is 2 by 2, minus the system matrix phi. And if we do this matrix algebra for the 4 different elements, we should end up with a matrix, top row equaling lambda minus 1, the second row being 2, lambda plus 3. And we want to now find the determinant of that matrix, which is now a function of lambda. Lambda is a variable. And the lambdas that will satisfy lambda I minus phi equal to 0 are the eigenvalues of that phi matrix, but they're also the natural modes of this system's dynamics. You guys learned all of this in 310, correct? Eigenvalues. Was that a yes or was this a question? Both?
So I don't know if I remember correctly, but I thought it was like minus lambda I.
Okay, the question was, does it matter if it's phi minus lambda I or lambda I minus phi? So now maybe I am confusing you, but it doesn't matter. You'll have the same values for your, or you'll get the same expression. Can you convince yourself that it doesn't matter? It's equal to 0, so you could add and subtract those quantities and put it on the other side, and then you have phi minus lambda I. Its determinant. And the determinant of a 2 by 2 is simply the product of the diagonals minus the product of the off diagonals, which in this case is lambda times lambda plus 3 minus the product of those two off diagonals. And we end up with lambda squared plus 3 lambda plus 2, which should make us feel very comfortable because that's what we had in our characteristic equation before, or our characteristic polynomial. That's the characteristic polynomial. When we set it equal to 0, it becomes the characteristic equation. And that's what we had done before. And now it's kind of fun because you have all these different ways of finding the answer in the back of the book. Somebody can work it one way and somebody can work it another way, and you can compare your answers. They're equivalent. But you didn't work it the way I did. Well, that's okay. Unless I tell you to work it a certain way, which I probably will not do. That's where we should have made it at least to that. Actually, we should have been further than that on Monday, but we're at least getting close. But now what we want to do is move from that time domain description into the frequency domain with our block diagram. We want to take this time domain all delay block diagram and generate a frequency domain block diagram. And the way that we do that, it's again fairly easy. All it takes is an eraser and some lead or pen, a writing tool. We simply erase unit delay in all of those blocks. We also want to erase all of the labels of the signals because we don't want to have mixing time domain and frequency domain signals. But we erase time domain in our unit delay blocks and replace those with z to the minus 1s. I was cheating. Before class, I simply copied this block diagram. And this should look exactly like what we had before. Now what we want to do is pull out our eraser which I have a little different way of erasing, but I'm going to, Now that one's gone, and I just need to erase this one. So I didn't use any eraser. Saved that. Have to be sustainable in this day and age, so we're working on sustainability. Now what we do is we simply replace or put into those boxes this operator z to the minus 1, and we're subsequently going to learn what that z means, or get a better feel for what z means later. But now we can label the output as the transformed version of little y. So now we just have to hit the shift key. We need to capitalize. This is now capital Y of z. Coming in, our input is now capital R of z. And what we really want now is a transfer function in terms of these coefficients in the z's that connect R of z and Y of z. We want to find a ratio of z's, polynomial in z, that will give us the transfer function between the input R and the output Y. We want to perform some block diagram algebra. And one of the, I know you will feel like you're chasing your tail when you're doing block diagram algebra if you haven't done it before. Sometimes you just keep saying, well, I can't seem to get what I want. But what we want to eventually end up with in this situation is one equation that involves only R's and Y's. Those are the only signals we've labeled at this point, but a lot of times it's more convenient to begin this process by focusing on signals that are the outputs of your summing junction, summing junctions, if you have multiple summing junctions. And write your signals in terms of those, and then try to substitute out everything except R's and Y's. Let's see if we can write an equation in terms of E of z, the output of that summing junction. And there's maybe not one unique way to do that, but I'll do the hard part. E of z is R of z. What are we doing? We're trying to now find equations for all the signals that are coming into that summing junction. We have the output of that summing junction. That's capital E of z. We now need to express all of the inputs. And it may be easier to try to write all of those in terms of E of z. So now I might look at this one and say, oh, I need this one. Well, that's this guy. And if I go all the way, whoa, I am chasing my tail. That was not quite what I wanted to draw, but I have this. Do you see that I can now write that signal that's coming into that summing junction in terms of gains, z to the minus 1s, and E of z? Or I can rewrite this as minus 3 z to the minus 1 E of z. That's this term. If I do this as something similar to the next input, that's this guy. It's minus 2, and I could just stop there, but and write it in terms of another labeled signal there, but I really want to keep going. And that's now my next expression, which is equal to what? Minus 2 z to the minus 1 times z to the minus 1 E of z. So I went all the way back to E of z. And then I was able to say that's far enough. Are we comfortable with where this one equation came from? We're simply setting the output of the summing junction equal to all of the inputs. And this will allow us now to actually solve for E of z. Let me write this as E of z is equal to R of z minus 3z to the minus 1 E of z minus 2 z to the minus 2 E of z. And now I want to put all of the e's on one side of the equal sign. So I add 3z to the minus 1 e of z, and I add 2z to the minus 2 e of z to both sides, and I have 1 plus 3z to the minus 1 plus 2 z to the minus 2. Those are all the scalings of e of z, and that's equal to r of z. That now allows me to go ahead and solve for e of z, which is 1 divided by 1 plus 3 z to the minus 1 plus 2 z to the minus 2 r of z. And this is actually a transfer function associated with this system. It's the transfer function between the reference input r and this other signal that we labeled E, which you might consider maybe an error signal. Or if I wanted to call that transfer function, let's say g sub E of z, which is the ratio of this arbitrary output or signal E over R. Do you see if I divided both sides of that black equation by R of z, I would end up with my transfer function that I now am labeling g sub E of z. It's now 1 over 1 plus 3 z to the minus 1 plus 2 z to the minus 2. And you may not like transfer functions written in terms of z to the minus 1s. You could factor out a z to the minus 2 from all of those terms downstairs, and a z to the minus 2 downstairs is like z squared upstairs. Or you could multiply by 1. Maybe this is something that seems a little easier. There's my 1, z squared over z squared, and that allows me now to rewrite that transfer function in terms of powers of z, z squared plus 3z plus 2. That's not the transfer function that we wanted, but it's one transfer function. And I think a homework problem asks you to find 3 different transfer functions from the same block diagram. And this sort of illustrates that you can at least find 2 from this one. What I've really done is I've said, oh, let me call this signal another output. That's sort of what I've done. But we wanted to find y of z as a function of r of z. Do you see how we might be able to do that now from looking at the block diagram? Can you see a relationship between y and e? Because we have a formula for e and in terms of r, e in terms of r. If we can now find a relationship between y and e, we have what we want. What's y in terms of e? Z to the minus 2 times e of z is y of z. Whoa. So notice that y of z is z to the minus 1, z to the minus 1, e of z, which is just z to the minus 2 e of z. Or we can now say that z to the minus 2, and we can replace that with what e of z was equal to, which was 1 over 1 plus 3 z to the minus 1 plus 2 z to the minus 2 r of z, which gives us then z to the minus 2 over 1 plus 3 z to the minus 1 plus 2 z to the minus 2 . And that's now our transfer function in the square brackets between the reference input r and the output y. In this class, our convention is probably to work with polynomials in powers of z, positive powers of z. And we can do that again by factoring out a z to the minus 2 from the top and the bottom, and those cancel each other out, and we end up with what we want. Or we could multiply by our nice form of 1, which is z squared over z squared. You can always multiply by 1, any equation, and not change anything, so that we can end up with y of z equaling, up top we have z to the minus 2 times z to the 2. The exponents add to get z to the 0. That's 1. And downstairs we have z squared plus 3z plus 2. And this is our g of z. And now we've gone from difference equation to block diagram to transfer function to state space representation. We have all 4 of those representations, and we can sort of work our way back and forth between those. And we'll learn how to do that a little bit better once we start doing the z transform of difference equations. Yes?
Would you ever want like signals to be included in that transfer function?
So now the question was, do you ever want to have signals in the numerator or denominator of that transfer function? If it's a transfer function, the answer is no. We don't want any other signals. We just want polynomials of z. So we don't want to see an e in there where e might be a signal. We don't want to see another r sub 2. We don't want to see another y. We need to get rid of those. And that's when you might think you're chasing your tail, is trying to get rid of all of those signals or other variables to end up with a strict ratio of polynomials in z. That's what you want for a transfer function. Other questions? Now that we've been playing with z, let's see if we can understand a little bit more or find an interpretation of that variable z. And now we want to connect with what I'm hoping you're already very familiar with, which is the Laplace transform. Do you remember what a time delay looks like in a Laplace transform? Suppose we started with this. The time domain, I had a lowercase x of t. To find its Laplace transform, we know the definition of the Laplace transform is this integral. From t equals 0 to infinity, x of t, we weight that signal of time, x of t, with this complex exponential, e to the minus st, and integrate time out of that expression, or we integrate with respect to time. So we're looking at this information over the entire time horizon and somehow consolidating it down into frequency domain information. That's what this Laplace transform is doing for us. It's converting from the time domain, where we're looking at this signal for all time, and we weight it by this complex exponential, and that allows us now to collapse that down to some expression in terms of s, which contains the frequency domain information of x, whether x of t is a signal or an impulse response. If we delay that signal by an amount t sub 0, it can be shown, and you should be able to find this in your 320 textbook, for example, this, or in a transform pair table, you should see this property that relates the time domain delay of a waveform with its frequency domain counterpart. To find or to move into the frequency domain, we simply have to scale that original transform, capital X of s, by this complex exponential e to the minus t sub 0 s. T sub 0 was a fixed quantity. That was our fixed delay amount. S, again, is our complex frequency variable. That's what I'm assuming you already have in your toolkit. Walking into class, you've now carried this toolkit of Laplace transform techniques with you. You now know how the time delay, what it looks like in the continuous time setting. Let's now relate that to what we're doing in this class, which is discrete time. And one of the ways that we will be thinking in this class is in sort of these quantized amounts of delay, a sample period. We're talking sample periods now, or how far do we separate when we in time this distance between samples, and that's our sample period. If t sub 0 in our continuous time setting has a numerical value equal to one sample period, which we in this class typically call capital T, then a one sample period delay, which in this class we've said is z to the minus 1, would in fact equal this Laplace transform expression when we replace t sub 0 with that same amount of time, our sample period, capital T. So now we're saying that this S-domain quantity or expression, this complex exponential, is equal to z to the minus 1. They mean the same thing. They both correspond to the same amount of delay. And that's what we will then use to develop this relationship between the S-domain and the Z-domain. We know now that z to the minus 1, that represents a one sample period delay in the frequency domain for discrete time systems, is equal to e to the minus st, and t is our sample period that has units of so many seconds per sample. And typically it's fractions of seconds. We might be sampling at 10 milliseconds, every 10 milliseconds. So capital T would be 0.01. But that's 0.01 seconds per sample. Every sample occurs in a time amount of 0.01 seconds. Oh, maybe how many like to stand on your head? Aren't we in physical education class? Have to somehow kick the students or kick the class, and now that's my way of doing it. What in the world's he talking about? Why are we worried about standing on our head? Well, that's sort of what this equation is doing. It's an inverse. We have z to the minus 1 equaling e to the minus st. They're both upside down, sort of. Well, we can get those into maybe standing on their feet by simply finding the reciprocal of both sides and setting z equal to e to the st. So if you don't like looking at things upside down, the relationship or the connection between s and z is equal to e to the st. And z, if z to the minus 1 was a delay, what's z? That's one advance. Just like with the s, 1 over s was like a integration, s was like a differentiation. If we multiply a signal by z, that's like advancing it one sample period in the time domain. There's our definition or connection between S and Z. Yes? So we now have two different complex numbers, or two complex variables, an S complex number and a Z complex number. And what we want to do now is, when you have a complex number, what is that? We no longer are living on the real axis. We've now upped that one dimension. We're now in a plane. We have the real axis and the vertical axis, and that So now the question is, where does this come from a physical standpoint? I would say let's just focus on what we just talked about, which is this delay. So the concept of a delay in Laplace was this e to the minus s some number. And that's how I would like you to think about where this e is coming from now. It's coming because it's what is present initially as our scaling amount or our weighting amount in the definition of the Laplace transform. And so that actually factors out in that process when we introduce a delay. So I would just think of this e, and you will be able to, and we'll start looking at all these different series or infinite sums, And you could think of e to the something as some series representation if you wanted to. But for now, let's just view it as our definition of z in terms of s. And what you've just made clear, I hope, is that now we have two different complex numbers. Z is a complex number that we will use as a frequency domain operator, just like you went back and forth in Laplace. Did you like to analyze circuits in the time domain with differential equations, or did you like to do it in the frequency domain with S? Most of you like to do it in the frequency domain. Well, now we have another tool that you can put in your toolbox that allows you to work in the frequency domain when you have discrete time systems, and that's the Z. So now let's look at this mapping between these two complex planes. We have two complex planes, an S-plane and a Z-plane. Let's just sketch those. Here's the S-plane, and here's the Z-plane, where the horizontal is just the real component of this complex variable S, and the vertical component is the imaginary part of S. And we have exactly the same, well, it's not exactly the same, but this a similar way of parameterizing the second complex plane, which we call the Z-plane. The horizontal axis is the real component of Z, and the vertical axis is the imaginary component of Z. And if I had a number, an S complex number, let's say at minus 3 plus J2, we want to know where does that map into in the Z-plane when we know that Z is equal to e to the st. Where does it go? We want to start feeling comfortable. Hopefully we feel somewhat comfortable in the S domain with what that corresponds to. If we had a pole at minus 3 plus J2, if we have real coefficients, we have a conjugate pole at minus 3 minus J2. And if that corresponded to a signal, that's now a e to the minus 3t cosine of 2t like expression. Our mode of our oscillatory frequency, our damped frequency of oscillation is 2 radians per second, and our damping is minus 3. Where does that go? Well, all we really have to do is have an S, which we have, and we have to have a sample period t, and then that will map it into another complex number in the Z-plane. And we're going to find that that's going to map somewhere like that. Let's see why that's the case. And notationally, I'm going to be introducing a lot of different parameters maybe. I might call this S is equal to a real component minus sigma plus j omega sub d. In our case, that was this minus 3 plus j2. The omega sub d stands for the damped frequency of oscillation. So omega sub d, the d in the subscript, is a damped frequency. And let's just assume, when we need it, that our sample period, the number or the amount of seconds per sample, will be 0.04 seconds. Where does that put us in the complex Z domain? So now, using Z is equal to e to the st, or parameterize the way that we have parameterized S as minus sigma plus j omega sub d, now you need to get comfortable with complex exponentials. But you know how to play with exponentials. That t we can distribute through that minus sigma plus j omega sub d, and we end up with e to the minus sigma t plus j omega sub dt. But a sum in the exponent is the same as a product of exponential terms. Let's do that. So let's now rewrite this as e to the minus sigma t, e to the j omega sub dt. Just playing with complex numbers and knowing what we know about exponents. But we can actually make this look a little bit cleaner if we simply say, oh, that's some real number. Let me call it r. E to the minus, think what we had. We had sigma of 3 and t was 0.04. So that's just going to be some e to the minus number. That will give us a real quantity r. What happens in this other piece? Well, we might just collapse these two and call that a theta sub d. So that now z, instead of in rectangular form, we might like to write that in polar form or exponential form as r e to the j theta sub d. Where r is equal to e to the minus sigma t, and theta sub d is omega sub dt. And to bring us back to reality, to a physical example, let's plug in the numbers. Our example that we had started with, we said S was minus 3 plus J2. And we said our sample period was 0.04 or 40 milliseconds. Let's see what Z ends up being. Z is now E to the S, which is minus 3 plus J2 times T, which is 0.04. Or that's E to the minus 3 times 0.04 e to the j 0.08. E to the minus 3 times 0.04 is minus 0.12. E to the j 0.08. This piece is our real component, and this is in fact an angle in radian with units of radians. And I'm assuming that you can convert radians to degrees if you want to picture that, but this is now 800ths, and how many radians do you have in a full circle? 2 pi. So now you can relate 360 and 2 pi to convert that 0.08 into an angle in degrees, so that if we looked at e to the minus 0.12, that ends up being 0.887, and that's e to the j 4.58 degrees. In the z-plane then, We are not quite all the way out to 1. We're at 89% of the way to 1, and we're up. The angle is measured with the positive horizontal axis at an angle of 4.58 degrees. We're now at this point, let's say right here. That's probably not very accurately drawn, but I'm overemphasizing. This distance is 0.887, and this angle is 4.58 degrees. Question? Yes, so you could, the question was, do we have to use exponential notation? Can we use polar form? Can you just say 8.87 at an angle of 4.58? That's fine. And at some point, you might want to convert that to rectangular. So you're going to need to get very comfortable going between rectangular and polar representations. So polar form would be 0.887 at an angle of 4.58 degrees. That's fine. What are some observations? And so when we were over here at minus 3 plus J2 in the S-plane, that mapped over here into another quadrant. It's now inside the unit circle. It has an a radial distance away from the origin of 0.887, and it has a little angle to it. If we had started on the real line, let's say right at minus 3, do you see where we would have ended up with? We would have ended up on the real axis in the complex z-plane at that same radial distance away from the origin. Because we had a rotation off of the real axis in the S-plane, we should expect a complex point in the z-plane. And we ended up off the real line in the z-plane. What kind of observations can we bring from that? Question. Oh, I'm going to write down a list of observations. So who knows whether I'm asking a question or just expounding? Huh. So now let's look at observation number 1. R, in our case, was e to the minus 3t. We had a negative exponential, and that means that that's going to be less than 1. The fact that we had a negative exponent for our radial distance put us inside the unit circle. And you can sort of see that if you looked at, let's say we call this real part of S, which is x, and we draw a curve e to the x. This is our e to the x curve. And what's this point right here? That's when x is equal to 0. What's e to the 0? E, anything to the 0 is 1. And over here, we would have a negative exponent, and on this side, we would have a positive exponent. That's supposed to be a flat line of distance 1. Anytime we're in or have a negative exponent, we are going to have a value for r less than 1. So we're mapping into the unit circle. And if we think about this in terms of the complex S-plane, if we had something in the left-hand side of the complex S-plane, that's actually mapping into the unit circle. And that's consistent. We know that we had stable, continuous time systems when the poles were in the left half of the complex S-plane. Everybody remembers what E is, right? 2.718, and it just keeps going. That's one observation. What's another one? Another one is that values of S, this is really what I was sort of making in a picture in observation 1. In observation 2, I'm just stating it verbally. Values of S in the left half S-plane map to values of Z inside the unit circle. We defined this new variable, theta sub d, which was this product of omega sub d and capital T, theta sub d is actually some angle. What are the units on these variables? What are the units on, let's start with T. That one I've told you today, I hope. This is seconds per sample. What about omega sub d? Well, that's radians per second. No. Pardon? I don't know what I said. I did say no, and I confused myself. So I should have said yes. So omega sub d is radians per second, right? That's the same units as omega sub n of radians per second. Maybe I was... So omega sub n is the natural frequency. That's the distance from the origin in the S-plane. Omega sub d is the vertical distance, or the imaginary component in a complex number. Now, if we multiply radians per second times seconds per sample, what do we get for the units on theta sub d? Radians per sample. Pictorially then, what we're saying is here is our real part of Z. This is our Z plane. And if we have a generic complex number that's in polar form, a distance r away from the origin and an angle of theta sub d, then at each sample, we are actually spinning or rotating around in this z-plane. Because theta sub d is the radians per sample. So the first sample, we're at, let's say, 4.58 degrees. At the second sample, we're at 4.58 plus 4.58, or about 9 degrees. And we just tick our way around that circle in the z-plane. We're spiraling in or out depending on what r is. If r was 1, we would be stuck on the unit circle and we would just be moving that amount of angle, theta sub d, at each sample. Observation 4. this was our rule of thumb that we've been talking about. We select our sample period, capital T, to be 30 times the closed loop bandwidth. For example, suppose we want a closed loop bandwidth of 5 radians per second. I.e., we want omega sub c, so I'm really playing with the subscripts on omega, aren't I? But omega sub c is our c for closed loop. Omega sub c is 5 radians per second. And if you wanted to think, if you're not comfortable with radians, you could translate that into cycles per second or hertz. Omega sub c is 2 pi f sub c, or f sub c is now omega sub c over 2 pi, and 2 pi is bigger than 6. It's 6.28. So this is now going to be 5 over 2 pi, which is a little bit less than 1. This is now 0.7978 hertz, or cycles per second, or samples per second. Maybe it's easier to think about frequency in samples per second. So this is now not at 1 hertz, it's a little slower than that. This closed loop bandwidth of 5 radians per second. We use that closed loop bandwidth, omega sub c, to figure out how fast we sample with omega sub s. Omega sub s is now 2 pi f sub s, which is 2 pi over t, and we want that to actually be 30 omega sub c. And you could play with the units if you want to. Omega sub s is radians per second. F sub s is cycles per second or samples per second. 2 pi is radians per cycle or radians per sample. And t is seconds per sample. Anyway, if we now use this piece over here to solve for t, t becomes 2 pi over 30 omega sub c. And pi, if I'm finding capital T, I can make capital T smaller without as much impact as making it bigger. You want to probably err on the side of making T smaller. So 3 is a little bit smaller than pi, is it not? So here's my approximation that I'm using. 2 pi, instead of 3.14, I'm just going to say that's 3, because that's easy to divide 30 into 3, or a little easier, and omega sub c was 5. So that now I have 3 and 30, I have 1/10. I have 2 over 10 times 5, or 2 over 50, or 4 over 100, or this is now my 0.04. What?
You went the other way than we were expecting. We were anticipating like 1 over 25 or
Oh, no, it wouldn't be that simple. I wasn't trying to reduce. What I was trying to divide by 100. I needed to up that denominator instead of reduce the fraction. I'm always trying to keep you guessing, right? But what have you just found? You've now found the sampling frequency in hertz. It's 25. What is 0.04? That's the sample period. So every 0.04 seconds or every 40 milliseconds we're sampling, which means that we're sampling how many times in a second? 25. So now this t is 0.04 seconds, which is 40 milliseconds, or the sampling frequency in hertz, or cycles per second, is 1 over t. And now you're really going to like this if you like the last one. This is now 1 over 4 over 100. There's the 25 hertz. Yes. I don't know. Sometimes the question was why did I leave the T out of this subscript business? I don't know. Sometimes I'll put a S on the T, sometimes I won't. So you'll see it either way, but that's the sampling period. This is the sampling frequency, and omega sub S is 2 pi times 25, which 25 is easier to think about in hertz. Question? So the question was, can we always be taking this liberty at, so typically when we have pi, it might be easier to simply round it to 3, because t is what? The rule of thumb. That's kind of flexible. But what I did was I actually made capital T smaller by rounding down from 3.14 to 3, and making the samples closer together is smarter than making it bigger. I'll see you on Monday, if not before.